How can you cause a current to flow through a wire without having actual source of EMF? Yes, this is possible by the phenomena of electromagnetic induction. What is electromagnetic induction? When a magnet and a wire move relative to each other. What does that mean? That is, either wire moves towards or away from the magnet, or magnet moves towards or away from the wire. A voltage or EMF is induced. Amount of induced EMF depends upon how much faster they move relative to each other, how much stronger is the magnet, and the shape of wire. Means if you have more coils, single instead of having single coil, you will get more EMF, that is high voltage. Here, this is the coil through which is connected to a voltmeter. Right now, there is no current in the coil. Voltmeter is showing zero. This is zero centered voltmeter. So, what happens when a magnet is moved towards the coil? If the magnet is moved into the coil, a voltage is induced across the ends of the coil, and zero center voltmeter deflects to one side. And this is momentary deflection, because when the magnet stops moving, the flux of the magnet through the coil is constant, so no EMF is induced. That is why the galvanometer or voltmeter will show zero deflection. Okay, so till the magnet keeps on moving, the galvanometer or voltmeter will show the deflection to one side. If the pole is reversed or the direction of motion is reversed, like instead of moving north pole towards the coil, we move south pole, or we take the magnet away, the direction of induced EMF will also be reversed. And that too again, because then the magnet stops moving, the voltmeter shows zero. So this is momentary deflection. When the magnet stops moving, the meter shows zero deflection. So electromagnetic induction also occurs if the magnetic field is stationary, that is, magnet is not moving and coil is moved towards it. So this is another way. This is the coil which is moving upwards, and it is cutting the magnetic field lines. So EMF will be induced. If it is a straight conductor, only the EMF will be induced across the ends of the conductor. But it is a complete wire loop like shown here in this figure, and it is moved upward. The voltmeter will show deflection and the EMF is induced. So this phenomena is called electromagnetic induction. And the direction of induced current is found out by Fleming's right hand rule, where the thumb shows the motion. Here thumb is pointing out in upward direction because the wire is moved upward, field from north to south, so the current is outward. Here, this is not a complete loop of the wire, it's only a conductor. So when it cuts the magnetic field lines, what happens? The EMF will be induced, that is, the charges, one end will be the positive and the other end will be negative. So here the Fleming's right hand rule is elaborated, that is magnetic field B, first finger, and direction of the motion of the wire, or that is thumb. Thumb indicates the direction of motion, and the second finger induced direction of induced current. So here when we move the magnet into the coil, it is difficult to push the magnet into the coil when there are more loops. Like in second and third loop, the figure, the loops are more. So the stronger the coil will have the current flowing through it, and that current in turn will have its own magnetic flux, which will move the, which will oppose the motion of the magnet towards the coil. In with two coils, the current is smaller, so magnet can be pushed in easily. In the second one, there are four turns in the coil, so it is difficult because the current will be larger, induced current will be larger, and that will also have its own magnetic flux, which will oppose the motion of the magnet into the coil. The size of induced voltage increases when the speed of movement increases, the strength of magnetic field increases, the number of turns on the coil increases, and the area of the coil is greater. Faraday's law. The Faraday's law of electromagnetic induction, what it states that is the induced EMF in a conductor is directly proportional to the rate of change of flux linkage. Flux linkage means how many field lines are there, and it is cut by how many number of coils. So the formula is E is equal to N delta phi change in flux divided by time. So rate of change of flux. So when a magnet moves past different materials, the induced voltage will be the same in each case. But the current, the larger current will be flowing through the wire, which is a better conductor, which has more loosely bound electrons. Like magnet will produce, the movement of magnet will produce larger current when it passes through when we use a copper instead of iron. There are some ways to change the flux because the induced EMF depends upon the rate of change of flux. So flux can be altered by many ways. So here there is a loop of wire, and we can increase or decrease the area through which the flux is passing. Here the cross lines are showing magnetic field into the paper, into the laptop screen. That means the laptop screen is like south and the north is opposite to it, and they are entering. So we can change the area of the loop by rotating it or by pulling it outward. So when we pull it outward, the area decreases. So flux also through the coil decreases. So the change in flux. Earlier, there was greater flux, there were greater free lines passing through the bigger area. When the loop is stretched, the area has become smaller, so induced current will also be smaller. One more way, we can spin the coil, we can rotate the coil, and we can change the flux through the coil this way. So the flux decreases. Either flux through the coil increases or the flux through the coil decreases. In both the case, the EMF will be induced. Here, there is third way of inducing EMF, not necessary to move the magnet towards the coil. We can have an electromagnet. So first coil is an electromagnet which has its own flux, okay, which is linked with the coil 2. Coil 2 doesn't have any battery in it. But when we change the current by means of a variable resistor R, what will happen? The current will change, and so will the magnetic field lines. For larger current, there will be more magnetic field lines of coil 1, which will be linked with coil 2. In the same way, for a smaller current, there will be fewer field lines. So we can constantly adjust the position of the rheostat or variable resistor. We can keep on increasing and decreasing the current constantly, and we can vary the magnetic flux through the coil 2, and EMF will be induced. The faster the current changes, the more will be the EMF induced. In the same way, if we are using magnet, then the faster the magnet moves towards or away from the coil, the greater will be the EMF. So what is the direction of induced EMF? This is explained by Lenz law. An induced current is always in such a direction as to oppose the motion or change causing it. So what was the change causing it in the first figure? Where the motion of the magnet towards the coil. Okay, so what will happen? The coil will have the direction of current in such a way that it will oppose the motion of that particular pole of the magnet. So minus sign here indicates that the induced current opposes the cause. So here the direction of induced current can be found out when we move the magnet towards the coil. So here the current is flowing in anti-clockwise direction through the coil. The end of the coil facing the north pole of the magnet has current in anti-clockwise direction, and the deflection is towards one side here. And the we know that when the current flows in anti-clockwise direction, that end is north pole. So it opposes the movement of approaching magnet. In the same way, this end is north pole and the other end is south pole. In the same way, when we have a magnet which is going away from the coil, the north pole is going away. In the previous figure, the north pole was approaching the coil, and here the north pole moves away from the coil. So the direction of current is reversed. And now it is the end of the coil which is facing the magnet is now having current in clockwise direction. So that is the south pole which will be formed at this end. Current anti-clockwise direction, the end is having north pole at this end. So it tends to stop the movement of north pole approaching it. And in second, it means it is repelling it. And when the current in the second diagram is in clockwise direction, that means the end of the coil facing the magnet is south pole, and it uh, opposes the motion of the magnet. It attracts the magnet towards. So tends to stop the motion of that north pole, which was going away from it. So in both cases, magnet moves against a force. A force will be acting on the magnet, either repelling force or attracting force. Okay, force may be attracting or force may be repelling, depending on the direction of motion of the magnet and the type of the pole. The induced current will induce in that. First one, north pole is induced at that end of the coil just to repel it, repel the approaching north pole. And the second one, that is attracting the north pole, which is receding it, which is going away from it. So work is done during the motion and it is transferred into the electrical energy. So that is actually the cause of the induced EMF. Work done is appearing in the form of electrical energy. Now here there are some questions related to Lenz law. Here in the first part, the north pole is approaching the coil, and in second part, the magnet is inside the coil, and third part, the magnet is moving away from the part. Indicate the direction of induced current I in each case and explain briefly. Don't worry, we have answer of this in the next slide. Indicate the first one, the direction of induced current. What is the direction of induced current? When the magnet's north pole is moving into the coil, that end will become north pole to oppose the motion. So induced current will flow and the north pole will be generated. Lenz law. Okay, so it opposes the approaching of the magnet. Second part, the magnet was inside, so induced current will be 0, and it is changed. It's going to change the direction if it's the magnet is in motion. If magnet is stationary inside the coil, the induced current will be 0 because there is no change in flux through the coil. Flux is constant, no matter how much large the flux is, no matter how many field lines are there, the flux is constant, no EMF will be induced. But if the magnet is in motion, the flux through the coil will be changing, or flux being cut by the coil is changing. So in this case, the magnet is the galvanometer or the voltmeter is showing 0 deflection. Now third part, the magnet is leaving, going away. So south pole is going away from it. So in order to stop this movement of south pole away from the coil, this end of the coil will have current in such a direction that and becomes north pole to oppose the motion of the leaving magnet. So here again there is a question. Use the right hand grip rule. You remember right hand grip rule for the solenoids. We can find out the polarity of the electromagnet by using right hand rule. The thumb indicates the north pole, and the fingers are curled around the wire, indicating the direction of current. Okay, so and Lenz law to predict the magnetic poles formed by the coils below in each case. So here, this is the north, and what will happen here in the coil? Let us see. We have the answer. No, we have to solve it ourselves here. So right, when we use the right hand rule, what is happening here? Uh, Holding this magnet in our hand, you can see the north pole is approaching and the current is in anti-clockwise direction. It is marked here. Okay, so current is in anti-clockwise direction means this end of the coil has become north. Second figure, because north pole is going away from it, so current is flowing in clockwise direction and this end become as south pole. Okay, so we can get the, when we hold this coil in our right hand, this end is north and this end is south. When we hold the coil in our right hand here, this end is north. Now here you have to predict the poles and the current direction for each of the following. Figure 1, what will be the pole when north pole is moving towards it? It means the upper one will also be the north pole. The end facing the magnet will be the north pole and current will be flowing in anti-clockwise direction. In second figure, since south pole is approaching, so the current will be flowing in clockwise direction. That is, in this first figure, the current will be flowing in this direction, that is to make the north pole means anti-clockwise this way, and here to make it south pole the current will be flowing in this direction to repel this approaching south pole. And here in the third figure, since north pole is going away, so soon this will become, it will be south pole. So south pole is formed when the current is flowing in clockwise direction. And in this fourth one, south pole is going away. So stop the motion of the south pole, the current will flow in anti-clockwise direction so that this end becomes north pole to attract this magnet which is going from away from it. And here the coil is moving towards the stationary magnet. So what will happen? To oppose the motion of the coil, the upper end will become north pole, means the current will flow in anti-clockwise direction. That is this. And here the current will be flowing in because it's going towards the south pole. So south pole will only repel the south pole which is above it. So this end will be having current in clockwise direction. That is, this is the arrow here, current clockwise, upper one, okay, anti-clockwise. So this is the answers are given here. Let us go to the next slide. So Lenz law makes sense if we think about the conservation of energy. If the opposite poles is formed, means that will attract the magnet's motion. Okay, it will, suppose north pole is approaching and the coil has south pole in it due to the clockwise direction of current, then this is against the law of conservation of energy, because it will attract, magnet will move faster and without doing any work the magnet will move towards the coil. Okay, so it means in order to produce an EMF, we have to apply, the greater force must be applied to move the magnet through the solenoid than through open space, as some of the mechanical energy is being converted into electrical energy. Okay, so here the energy comes from the mechanical energy, that is the motion of the magnet. Okay, in order to move the magnet towards the coil, the work has to be done. If the coil has opposite pole formed to that of the approaching magnet, then it will automatically attract the magnet towards it. It means we cannot, like, we don't need to apply force. It will go towards the coil itself. Is this in this, if the upper end becomes south pole, so you don't need to do the work, it will, magnet will be attracted by the south pole, so the upper end becomes north pole. So we do need to apply force and we do have to do work on the magnet. That mechanical work appears in the form of electrical energy. So there are some applications of this electromagnetic induction. So one of the application is alternating current generator, that is AC generator. There is another one more video which was uploaded earlier, and that was in having more detail of the AC generator, how it is constructed, how the EMF is induced. All is there in that video, but there is some brief discussion of the AC generator. Okay, so the electricity is produced by generator effect. Okay, and the simplest AC generator, this is the diagram of the AC generator, where the coil moves between the two poles of the magnet. These are the commutator rings, and the current through the coil keeps on changing the direction due to the rotation of the coil. So coil has to rotate within the magnet. So you may watch the other video in which the detailed explanation is there. The output of the AC generator is not constant, it's not steady. It is a varying current, voltage varies. Okay, it increases, becomes maximum, decreases, and then becomes zero, and then reverses the direction. So peak voltage is obtained when the coil is horizontal, because moving this side is moving upward, and we may call it A, B. AB is going up and CD is going down, because the coil is rotating in clockwise direction. Okay, so side CD will have current. In particular, if you apply Fleming's right hand rule, so field towards south and motion upwards, so the current, induced current direction is this. And it means the other side, because motion is down, so induced current direction will be this. So this one is attached to this commutator. So this commutator is positive and this commutator is negative. After half cycle is completed, the direction, the coils, the sides of the coil will switch. CD will go to this side and AB will be there on that side. So then this one will be negative and this one will be positive. So this is the output shown. For horizontal orientation of the coil, the voltage is maximum. And for vertical orientation of the coil, almost no field lines are cut by the motion of the magnet. So voltage is zero. When the direction of sides are reversed, the voltage, induced voltage, will also reverse. One complete cycle is from peak to peak. So this is the coil vertical. It cuts almost no flux when it is vertical. So EMF is zero. At horizontal motion, the maximum EMF is induced. At vertical, again, no EMF. At horizontal, again, the EMF induced is maximum. So generator converts mechanical energy into electrical energy, where motor converts electrical energy into mechanical energy. So an alternating voltage is induced in the coil, and by means of the two slip rings, we can get output. The current will be flowing in opposite direction after every half cycle. The faster the coil is rotated, the greater will be the magnitude of the induced EMF and induced voltage and current, and the higher will be the frequency. So this is bicycle generator, which due to the rotation of the wheel, what happens as the wheel turns, the magnet also rotates and it cuts the flux through the coil is changed. Okay, so this electromagnetic induction occurs and alternating voltage is induced in the coil. This causes alternating current to flow through the coil and the light bulbs operates. This is another diagram of AC generator. The steam turbine will rotate the coil, and the rotation of the coil will induce EMF and the bulb lights up. Now this is the question. You have a voltage of a generator that varies in time using the same set of axes. You show how the voltage would vary if the rotational speed of the generator was doubled. So when the rotational speed is doubled, of course, the voltage will increase as well as the frequency. There are more waves per unit time. You can see first wave, it was having uh, one In half cycle of the first wave, there is a complete cycle of the second wave. Now here there are some questions to solve. To fill up, the dash effect occurs when a conductor is moved relative to dash. The generator effect occurs when a conductor is moved relative to magnetic field. This is also known as electromagnetic. What will come from there? That is induction. The greater the relative dash of the conductor and magnetic field, the dash is the voltage. The greater the relative movement of the conductor and the magnetic field, the greater is the voltage induced. If the conductor is a part of a dash circuit, an electric current will flow. Current will flow only when the path is complete. If you have only a rod which is moving through the flux, then the EMF only will be induced. You will have one positive sign at one end and positive charges and negative charges at the other end, but current will not flow. So for the current to flow, there has to be a complete circuit, that is complete path for the current to flow. So dash current is produced if the direction of movement is constantly dash. So alternating current when it is constantly reversed means alternating current has varying current, varying magnetic field will be associated with it. Now the transformer. Transformer is a device that is used to change the alternating voltage level to another. It means it may increase the voltage of alternating supply, or it may decrease. So these are the some diagrams of this uh, transformers. And this is symbolic diagram. One coil is primary and the other one is secondary, but this is primary coil, secondary coil. Primary coil has to have a source of EMF, and the secondary coil doesn't have the source of EMF. It has induced EMF due to relative change in the flux. Okay, so it is connected to a voltage source, but that in order for the current to be induced in the secondary, there has to be a variable resistance so that the current is varied, because this is the DC supply. Okay, but if you connect the voltage to the AC supply, the current will change itself. DC means you have to connect a variable resistance. Okay, but there are 2 points, two moments when we can get the induced current. The moment when we turn the switch on, the current starts flowing and there will be flux associated with it. So that the galvanometer will show momentary deflection. And the next moment will be what? When the current is switched off, switching on and off. Okay, then the galvanometer or voltmeter in the secondary coil will show deflection. Only that is a possibility in this case, because there is no rheostat or variable resistance connected. So the constant current, the flux will be constant, and constant flux does not induce EMF. Okay, and when we have a coil, iron core inside, so the more field lines will pass through, more of the field lines of the primary will pass through the secondary, and the greater will be the EMF. But again, if this is the AC source, we don't need to vary the current. But if it is a DC source, then we have to make some arrangement to vary the current constantly. Okay, instead of switching DC voltage source on and off, we can have AC voltage. Okay, so the rate at which the magnetic flux changes, that is the frequency of the alternating current. So now the proper structure of the transformer it consists of two coils of wire wrapped around a laminated iron core. So this is a laminated iron core. This is the coil. We call it primary coil. It has n number of turns, and this is the secondary coil. This has number of turns. We call them NS. This is NP, number of turns in the primary. Okay, so and this is the laminated iron core, because iron core will keep the field lines concentrated. It will transfer maximum flux of the primary to the secondary. So when input voltage is applied, alternating voltage is applied, the flux in the, we call it primary voltage, and the flux will be generated and EMF will be induced in the secondary. Okay, and amount of EMF induced in the secondary depends upon the number of coils in the secondary. Since in this diagram it has less number of coils in the secondary, so the voltage which is induced will be less than the voltage in the primary. Okay, so flux will change because the alternating current does not have constant magnitude. The magnitude of current varies, the number of field lines will also vary. Okay, increasing current will have more field lines and decreasing current will have less number of field lines. Change in flux has to be there. How does a transformer work? When alternating voltage is applied to the primary coil, of NP turns, it causes an alternating current to flow in the coil, and this current causes a changing magnetic field in the laminated core, iron core, which cuts across the secondary coil, which has NS turns. So, electromagnetic induction occurs in this coil, which produces an alternating voltage. Now, the questions related to it: why can a transformer not change the level of the voltage output of a battery? A battery produces steady current, and the voltage would cause a constant direct current. The flux will also be constant, not changing. So, no current will be induced in the secondary coil. No electromagnetic induction will occur only at the time of switching on and off. So there will be no secondary voltage if there is steady current flowing through the primary. So transformer equation, the voltage or the potential difference across the primary and the secondary coil of a transformer are related by the equation, that is primary voltage over secondary voltage is equal to primary turns over secondary turns. This was the word equation. This is the symbolic equation. Vp primary voltage, Vs secondary voltage, Np number of turns in the primary, Ns number of turns in the secondary. Now questions. Calculate the secondary voltage of a transformer that has a primary coil of 1200 turns and secondary coil has 150 turns if the primary is supplied with 230 volts. So Vp is 230. So what will be Vs? So we will use this equation. Vp over Vs is equal to Np over Ns. So 230 over 230 is the primary voltage over Vs is equal to number of turns in the secondary 1200 and number of turns 150 in the secondary. Of course, the secondary voltage will be less. So that is 8 volt. Not 8 volt. This is the ratio here which is solved here. 1200 divided by 150 is 8. So what is the answer? 230 divided by 8 is 28.8 volts will be available in the secondary. Next question, calculate the number of turns required for the primary coil of a transformer if the secondary has 400 turns and the primary voltage is stepped up from 12 volt to secondary voltage of 48 volt. So secondary voltage is given here and the primary voltage is not given. Sorry, it is given. It is a step-up transformer. What is step-up transformer? Which has more number of turns in the secondary. Okay, so 12 volt in the primary and 48 volts in the secondary. So it means number of turns in the secondary will be greater. So 12 divided by 48 is equal to NP over 400. It's a ratio. So it will be 4 times less than the number of turns in the secondary. That is 100 turns. Secondary has 400, primary has 100 turns. So voltage turn, we call this equation also the voltage turn ratio. Okay, whatever is the ratio of the turns, same will be the ratio of the voltages in the primary and secondary. Now you have to complete some questions here. Voltage 230 volt and the turns are 1000 and the voltage in the secondary is 11.5 volt. So what will be the answer? You may solve it and get the answers. Here 50 turns. Now here the primary voltage and turns are given. What is the secondary voltage when the secondary has 100 turns in it? So 5 times less than this, because the ratio between 500 and 100 is 5. So it has 5 times less number of turns. So voltage induced in the secondary will also be 5 times less. So that is 46 volt. Here 230 volt and secondary has more volts in it, and turns are also greater. So 230, 920, how many times greater than 230? That is, it is 4 times greater. So output voltage is 4 times greater. So turns are also 4 times greater. It means here, what do you guess? This will be, I am guessing 200. Yes. Okay, now here the primary voltage is to be found out. Others are given. So same equation will be applied and the answer is 9 volt. Again, the last two examples are of step down, step up transformer. The upper ones are, first two examples are of step down transformer in which the output voltage is less and secondary turns are also less. And next two, last two are of step up, because see the primary voltage 230 and secondary voltage 920. Okay, and the next also, and power transfer, because transformer actually delivers power. Input power will be equal to output power provided the transformer is 100% efficient. Means input will be equal to output. What does efficiency mean? Output over input. If output is equal to input, means it is 100% efficient. The same will be the output power. Okay, so power is voltage into current. Then ip into vp is equal to is into vs. That is, current power in the primary is equal to power in the secondary. So calculate the primary current if when a transformer is supplied with 230 volt, the secondary provides 4 ampere at the voltage of 13 volt. Okay, so output voltage is 13 volt and the secondary current in the secondary is 4 ampere. So we have to calculate the current in the primary, where the primary voltage is 230 volt. Okay, so primary current is 0.226. So use this equation is only used when the transformer is 100% efficient, because in that case only the power input will be equal to power output. Now calculate the secondary current from a transformer supplying a secondary voltage of 6 volt. If the primary is supplied with a current of 0.2 ampere at 230 volt. Assume that the transformer is 100% efficient. So again, the transformer is 100% efficient, and the current in the primary is 0.2 and current in the secondary 0. Voltage in the primary is 230. So what is the current in the secondary? When it is again the step down transformer, because output is less than input. So it means current is being stepped up. When voltage is stepped down, current is stepped up. That is 7.67 ampere is the current flowing through the secondary of the transformer. Okay, here now we are going to use both the equations, that is voltage turn ratio and the power input and output power. Okay, these all are the examples of the 100% efficient transformer. So here NP and VP are solved. So first we have to calculate VS. What will be Vs? Using the equation Np over Ns is equal to Vp over Vs. When we solve it, what is the answer? 10 volt. And then using equation Vp into Ip is equal to Vs into Is, we will get the output current in the secondary. And because input current is smaller, so output current will be larger. Which equation will we apply here? That is, for the first part, to calculate Vs, we will use Vs over Vp is equal to Ns over Np. Okay, answer is coming 10 volt. And for this thing, that is to calculate the current, we will use Vp input power, voltage input into voltage, primary current is equal to Vs into Is. Okay, so we can get the answer using this. Uh, 8 ampere is the current in the secondary. Now, 100 volt, 100 turns in the primary and 12 volt. So this is step up transformer because the voltage in the secondary is 480 volts. So what will be the number of turns? Of course, they will be less. 100 turns are there in the primary. So secondary must be having more turns. That is 4000 turns. Okay, and what will be the current in the secondary? When the voltage is stepped down, current will be stepped up. We will use the second equation, that is 0.2 amperes the current. Now 372 volts. What is the primary current? Whereas the secondary voltage is not given. The number of turns in the secondary is this. So first, in this case, we will apply first the power equation to calculate the power, because we know the input voltage, primary voltage, we know the mm, we don't know secondary voltage, and we also don't know the uh, current in the primary. So what we will do in this case, we know the current in the secondary. So what if we apply Vp into Ip is equal to Vs into Is? We don't know both Ip and Vs. So how can we work out Vs? We can use, we will have to apply first equation, 372. So what will be Vs? We will apply Vp, Vs over Vp, or Vp over Vs is equal to Np over Ns. So this part will come, that is 12 volt, and then we will apply Vp Ip is equal to Vs Is. Okay, so voltage is stepped down and current is stepped up. 8 and 7, that is the last question of this. And what appears? Current is 10 ampere and primary current is 10 ampere and secondary current is 2 ampere. Means the current is stepped down. It means the voltage must be stepping up. So let us see, the voltage in the primary must be less. So what we will do in this case, we know Vs and Is, we don't know V. So we will use this equation first. That is Vp Ip equals to Vs Is. So when we use this equation, this is the current in the primary 10, and voltage in the primary is not known to us, and is equal to Vs 125 and Is 2. So what answer we will obtain? We can get it by solving it. That is, the answer will be 25 volts. Okay, because turns are not known. So we will find out the turns now using voltage turn ratio. So that is 50. Now let us go to the next slide. Step-up transformers. In a step-up transformer, the voltage across the secondary coil is greater than the voltage across the primary coil. So turns are also greater. So this is the diagram of the transformer, which is step-up transformer. This is used to supply the voltage to the industries where greater voltage is needed. So we use the increase the voltage from 25 kilovolt to up to 400 kilovolt. So step down transformer, it decreases the voltage, and it is for the appliances at home, okay, which need smaller voltage. Okay, like output from the main supply from 230 volt to 18 volt. We use like for the computer, laptop, etc. Okay. Iron core, it increases the efficiency of the transformer. Okay, because it will keep the flux concentrated within the region. It will transfer maximum flux of the primary to the secondary. Flux leakage will be minimized. It should be properly shaped iron core. Okay, so increasing the magnetic field, cores are laminated to reduce the inductance, that is eddy current loss, because the current will induce in the core itself, because core is also a conductor. So eddy current loss, eddy current will cause heating, and unnecessary heating will increase the resistance of the coil. So that is why we use the lamination, and we keep the laminations separate from like each uh, coil, each you can say disc or iron strip separate from the other by means of the lamination. Here, these are the laminations, so they are separated from each other. So current will not be, eddy current will be minimized. Okay, eddy current is the current which finds its way through the conductor. So iron is a, though it's not good like copper, but it is a conductor. So we use this type of lamination, and we join them together, and magnetic field can pass through the lamination. Transformer and the national grid. National grid is the system of cables used to deliver electrical power from power station to consumers. The higher the voltage used, the greater is the efficiency of the energy transmission. Okay, because the current will be smaller, it delivers power, Vp, Ip. If voltage is in the secondary is greater, the current in the primary will be smaller. So that will produce less heating. Lower voltage means higher current, because power has to be the same, Vp, Ip equals to Vs, Is. So higher current, and higher current will cause energy to be lost in the form of heat, that is I square R loss. Okay, Vp, Ip is equal to Vs, Is. Okay. If the transformer is not 100% efficient, we have to consider the efficiency formula. According to that efficiency, we can calculate the output. But the larger current, more I square R loss. Current, if it is increased, the power loss in the form of heat through the cable will also be increased, because the longer length of the cable, it will have more resistance, and the larger current will produce heating, and heating, the power will be dissipated in the form of heat. So this is 25 kilovolt, and it is increasing up to 130 kilovolt. A power station, at power station, the output voltage of the generator is stepped up by the transformer from 25 kilovolt to 132 kilovolt. Okay, and that may be increased further depending on the requirements. Okay, over the longer distance, it may go up to 400 kilovolts. And so the power transmission is carried out keeping the current low. The lower the current, the lower will be the power loss. Okay, so here this is the national grid system shown. The 33 kilovolt is the voltage produced by the transformer, which is delivering it to the factories. It is step down. This is for the houses. It is not step down in one step. It is step down. See the gradually 11 kilovolt voltage is delivered to light industry. Okay, and it is step down further, and 230 volt is supplied to the houses, that is consumers like us. Okay, the lowest voltage is 230 volt for domestic use. The final step down transformer will be at substation within a few hundred meters for each group of houses, because the current will be stepped up, voltage is stepped down, current will be stepped up, so length of the cable should be shorter. So that is few hundred meters away from the residential area. So why is electrical energy transmitted over the national grid in the form of alternating current? To maximize efficiency, high voltage must be used. Okay, this is the answer. Voltage therefore needs to be changed a level. Steady current cannot be stepped up or stepped down. So primary voltage, because we can use the transformer, we can step it up at various levels, we can step it down at other levels. Okay, so they will, and transformer works only on AC. So the transformers are used to change one dash voltage level to another. Why don't they do not work with dash current? So what will come here? Alternating voltage. They don't work with direct current. Step up transformers dash the voltage because their dash has more turns than the primary. The step-up transformer increase the voltage because their secondary coils has more turns than the primary. Transformers are used in the dash grid. The dash output of a power station is increased to up to dash. Let us see what comes. The national grid, the dash output 25 kilovolt output of a power station is increased to up to 400 kilovolts. A high voltage reduces the energy loss, power loss to heat due to the resistance of the power line. So that's all. And inshallah, we will see each other with other video. Till then, Allah Hafiz.